I want to start with a number that I think deserves more attention than it usually gets. In conversations about the search for extraterrestrial intelligence, it's 0. After more than 60 years of systematic searching, after pointing increasingly sensitive radio telescopes at thousands of stars and millions of frequencies, after scanning the sky for laser pulses and anomalous infrared signatures and structured electromagnetic signals, after analyzing billions of data points from observatories on every continent and from space, after dedicating careers and lifetimes and institutional resources to the question of whether anyone else is out there, 0 confirmed detections, 0 verified signals, 0 unambiguous evidence of any kind that any technological civilization has ever existed anywhere in the observable universe except here on this small rocky planet orbiting an ordinary star in the outer spiral arm of an unremarkable galaxy. Now, I want to be careful about what this 0 means and what it doesn't mean. It doesn't mean the search has been exhaustive. The universe is vast and our instruments are limited, and 60 years is a geological eye blink. There are frequencies we haven't searched, and stars we haven't examined, and signal types we haven't thought to look for. The absence of evidence from an incomplete search is not evidence of absence. But here's what I want to explore tonight in a way that I think most public discussions of this topic avoid. The 0 isn't just a data point about what we have or haven't found. It's a window into something much deeper about the nature of life and intelligence in the universe. And when you look through that window carefully, when you examine what we actually know about the conditions required for life and the probability of intelligence emerging and the physics of what happens to civilizations over time, the picture that emerges is not the optimistic one that science fiction has prepared us to expect. The picture that emerges is one in which the silence might not be a puzzle to be solved by better instruments or longer searches. It might be the answer. The universe might be telling us something we're reluctant to hear, that intelligence is extraordinarily rare, that the conditions that produced us were so specific and so improbable that we might be the only technological civilization that has ever existed in the observable universe. That the search for extraterrestrial intelligence might be a search for something that genuinely isn't there. I want to follow this possibility honestly, without the comfortable assumption that the universe must be teeming with life, because the alternative is too lonely to contemplate. Without the anthropocentric bias that says the universe would obviously produce many beings like us, because we're obviously so important, with just the evidence and the logic and the willingness to sit with an answer that is deeply uncomfortable but might be true. Let's begin. Let me start with the Drake equation, because it's the framework that has structured thinking about extraterrestrial intelligence for 6 decades. And because I think understanding where it has gone wrong is essential for understanding why the silence might be more significant than most people realize. Frank Drake wrote down his famous equation in 1961 at the first SETI conference in Green Bank, West Virginia. It estimates the number of currently active communicating civilizations in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the number of potentially habitable planets per star system, the fraction of habitable planets on which life actually arises, the fraction of life-bearing planets on which intelligence emerges, the fraction of intelligent species that develop detectable technology, and the average lifespan of a technological civilization. When Drake and Carl Sagan and other optimists plugged in their estimates in the 1960s and 1970s, they got answers ranging from thousands to millions of currently communicating civilizations in the Milky Way alone. The universe seemed obviously teeming with intelligence. The only question was how to find it. But here's what has happened in the 6 decades since Drake wrote his equation. We've learned enormously more about each of the factors in it, and Almost every piece of new knowledge has pushed the estimates down, sometimes dramatically. The first factor, star formation rate, and the fraction of stars with planets have actually held up well or improved. We now know that most stars have planets. Exoplanet surveys have found planets around the vast majority of stars we've examined. This part of the optimistic picture has been confirmed. But then you get to the factors about habitability and life and intelligence, and the picture changes fundamentally. Let me talk about the rare earth hypothesis, because I think it represents one of the most significant and most underappreciated developments in astrobiology of the last several decades. The habitable zone concept, the idea that a planet needs to be the right distance from its star to have liquid water, is correct as far as it goes. But it's become clear over the last 30 years of planetary science that being in the habitable zone is necessary but far from sufficient for a planet to actually develop and sustain complex life. Consider what Earth has that most planets don't. A large moon. Earth's moon is extraordinarily large relative to the size of Earth's. It stabilizes Earth's axial tilt, preventing the dramatic wobbles that would otherwise occur over millions of years. Without the moon, Earth's axial tilt might vary chaotically between nearly 0 and more than 85 degrees over millions of years, causing climate swings so extreme that its complex life would face repeated extinction-level events. The formation of a moon as large as ours required an extraordinarily specific collision between early Earth and a Mars-sized object at the right angle and velocity. This event appears from our solar system formation models to be highly improbable. A protective gas giant, Jupiter's gravitational influence has deflected or captured an enormous fraction of the asteroids and comets that would otherwise have bombarded the inner solar system. Throughout Earth's history, without Jupiter, Earth would likely have experienced impact events catastrophic enough to prevent the establishment of stable, complex ecosystems hundreds or thousands of times more frequently than it has. Our Jupiter is unusually well positioned for this protective role compared to gas giants in other planetary systems we've observed. Plate tectonics. Earth's active plate tectonics drives a carbon dioxide cycle that regulates global temperature over geological timescales. When CO2 levels rise, temperatures increase, causing more rainfall, which dissolves more CO2 from the atmosphere into carbonate rocks that subduct and release CO2 back into the atmosphere through volcanism, maintaining a roughly stable climate over hundreds of millions of years. Without plate tectonics, this self-regulating mechanism doesn't operate, and planets tend toward either runaway greenhouse conditions like Venus or permanent glaciation. Plate tectonics appears to require a planet of approximately the right size with the right composition of radioactive elements to drive mantle convection. Mars is too small. Venus, for complex reasons, doesn't have it. Magnetic field. Earth's magnetic field, generated by its iron core, protects the surface from the solar wind that would otherwise strip away the atmosphere and from cosmic radiation that would make complex life extremely difficult to sustain. Generating a magnetic field requires a planet of the right size with the right core composition and the right rotation rate. Mars lost its magnetic field early in its history and consequently lost most of its atmosphere. This is just 4 factors. Researchers studying planetary habitability have identified dozens of parameters that must fall within specific ranges for a planet to sustain complex multicellular life over the geological timescales required for intelligence to evolve. The probability that all of these align on any given planet, even one in the formal habitable zone of its star, is not well constrained, but estimates from researchers who have examined this carefully suggest it might be orders of magnitude lower than naive habitable zone calculations imply. The rare earth hypothesis developed by the paleontologist Peter Ward and astronomer Joe Kirchfink, among others, suggests that the conditions for complex life are so specific that simple microbial life might be fairly common in the universe, while complex multicellular life, and especially intelligence, might be extraordinarily rare. possibly unique to Earth. Now, let me walk through what I think are the two most important and most underappreciated bottlenecks in the development of complex life on Earth. The ones that, if you examine them honestly, suggest that the path from chemistry to intelligence involves improbabilities so extreme that they might constitute genuine one-time events in the history of the observable universe. The first is the origin of life itself. How does chemistry become biology? How does a collection of organic molecules in water transition to the first self-replicating system capable of Darwinian evolutions? We don't know. This is not false modesty. After decades of serious research into the origin of life, including the famous Miller-Urey experiments and subsequent work on RNA world scenarios and hydrothermal vent, origins and dozens of competing hypotheses, we still don't have a credible detailed account of how the first self-replicating molecule arose from prebiotic. It's chemistry. What we know is that life on Earth arose relatively quickly by geological standards, within a few 100 million years of the planet cooling enough to have liquid water. Some researchers take this as evidence that the origin of life is easy, given the right conditions. If life arose quickly on Earth, maybe it arises quickly everywhere with liquid water and organic chemistry. But this inference is fundamentally flawed by a statistical bias that I think is one of the most important and least appreciated ideas in astrobiology. It's called the anthropic shadow. The anthropic shadow works like this. We can only observe the origin of life from a planet where life actually originated. The origin of life is an extraordinarily rare event happening, perhaps once in 10 billion tries, then most planets with liquid water and organic chemistry never develop life. But the planets that do develop life, by definition, produce observers who look at the geological record and see that life arose quickly in their planet's history. Not because life always arises quickly, but because only planets where life happened to arise quickly by the available window can produce observers who notice. The anthropic shadow means we cannot infer the probability of the origin of life from the fact that it happened quickly on Earth. If it's a 1 in a trillion event, we'd still expect to find ourselves on a planet where it happened quickly, because those are the only planets we could be on. The apparent speed of life's origin on Earth tells us nothing reliable about the frequency of the origin of life across the universe. The second great bottleneck is the eukaryotic cell. For approximately 2 billion years after life originated on Earth, all life was prokaryotic. Simple cells without nuclei, without organelles, without the complex internal architecture that makes complex multicellular life possible. Then, approximately 2 billion years ago, something extraordinary happened. A prokaryotic cell engulfed another prokaryotic cell, and instead of digesting it, is established a symbiotic relationship. The engulfed cell became the mitochondria, the power plant of the eukaryotic cell. This single event, or small number of events, gave rise to all complex life on Earth. Every animal, every plant, every fungus is descended from this merger. Crucially, this event appears to have happened exactly once in 4 billion years of life on Earth. Not many times. Once. Despite bacteria having 2 billion years to stumble upon this arrangement, the eukaryotic cell appears to have been a genuinely rare accident, an event so unlikely that it happened only once in 4 billion years, even with the entire biosphere of an entire planet running billions of bacterial experiments simultaneously. If the eukaryotic transition is a 1 in a billion years event, then the number of planets in the observable universe that have transitioned from prokaryotic to eukaryotic life might be very small. And without eukaryotic cells, there is no path to complex multicellular life, no path to intelligence, no path to technology. Now I want to talk about intelligence itself, because I think this is where the most important and most uncomfortable truths about the likelihood of extraterrestrial civilization is live. intelligence is often assumed to be an inevitable product of evolution. The argument goes that intelligence confers such significant survival advantages that natural selection will inevitably produce it given enough time and the right starting conditions. Evolution tends toward complexity, and complexity eventually produces brains, and brains eventually produce intelligence. This argument sounds compelling, but it's wrong. And I want to be specific about why. Natural selection doesn't optimize for intelligence. It optimizes for reproductive fitness in a specific environment. Intelligence is just one of many strategies for achieving reproductive fitness. And it's an extraordinarily expensive strategy. Metabolically, the human brain represents about 2% of body mass, but consumes about 20% of our caloric intake. For most of evolutionary history, and in most environments, this metabolic cost was not justified by the reproductive advantages of intelligence. Consider the actual history of life on Earth. Complex multicellular life has existed for approximately 600 million years. For most of that time, life was dominated by organisms with minimal nervous systems. Arthropods were the most complex animals for hundreds of millions of years. Fish, and then amphibians, and then reptiles developed increasingly sophisticated nervous systems, but none of them developed anything approaching human-level intelligence. Dinosaurs dominated Earth for 165 million years and produced nothing we'd recognize as technological intelligence. Human-level intelligence arose exactly once in 600 million years of complex multicellular life on Earth. In one lineage of mammals within one taxonomic group of primates over the last few million years. Every other branch of the tree of life tried a different strategy. The biologist Stephen Jay Gould made this point repeatedly. If you replay the tape of life on Earth from 600 million years ago, the overwhelming probability is that the result would not include Homo sapiens or anything like us. It's intelligence as humans possess. It is not the inevitable endpoint of evolution. It's one particular path taken by one particular lineage under one particular set of environmental conditions. The extinction of the non-avian dinosaurs 66 million years ago was the event that opened the ecological niches that mammals eventually exploited and that eventually led to the conditions under which primate intelligence became advantageous. Without the asteroid impact, our lineage might have remained small insectivorous mammals forever, or might have been outcompeted by the avian lineages that did survive, or might have eventually produced intelligence on a very different timescale. The point is that nothing about the history of life on Earth suggests that intelligence is the expected endpoint of evolution. It looks far more like a highly contingent accident, a fluke, an event that happened to happen here under a very specific and improbable set of circumstances, but that might not happen at all in most biospheres, that otherwise satisfy all the conditions for complex multicellular life. If intelligence is a 1 in a billion species fluke, then you can have a galaxy full of planets with complex life and still have only a tiny number of intelligent species, possibly just one. Now, I want to introduce the great filter because it's the concept that I think cuts most directly to the heart of what the Fermi paradox is actually telling us. And because I think understanding it properly changes how you think about the question of, are we alone? The great filter is the idea developed by the economist Robin Hanson in 1998 that somewhere along the developmental path from chemistry to galaxy colonizing, civilization, there is at least one step so extraordinarily improbable that almost no planet ever passes through it. The great filter explains the silence. If almost no civilization makes it through the filter, then the galaxy is quiet because almost no civilization reaches the stage of being detectable. The terrifying question is where the filter is, behind us or ahead of us. If the filter is behind us, then humanity has already survived the hardest part. The origin of life, the eukaryotic transition, the emergence of intelligence. some combination of these events was so improbable that we're among the vanishingly rare survivors. In that case, the silence is explained and our future is potentially open. We might colonize our solar system. We might develop extraordinary technology. The hard part is already done. If the filter is ahead of us, then something catastrophically reduces the number of civilizations that pass through our current stage of development to essentially zero. Every civilization that reaches technological capability runs into something that destroys it with near perfect reliability. And we might be approaching that filter right now. The fact that we see zero evidence of any civilization that has survived to the galaxy colonizing stage is strong evidence that whatever the filter is, it works. Almost no civilization gets past it. The question of whether we're before or after it is the most important empirical question about our species' long-term future. And here's where I want to be honest about what the evidence suggests. The optimistic position is that the filter is behind us, that the origin of life and the eukaryotic transition and the emergence of intelligence were all extraordinarily improbable, and we got lucky. In that case, we're rare survivors, and the galaxy is mostly empty of intelligent life. But there's a deeply unsettling implication of this position. If the filter is behind us, and we're cosmically rare, then finding even simple microbial life on Mars or Europa would be genuinely terrible news. It would mean the filter isn't at the origin of life. Mars had liquid water for hundreds of millions of years, and if life arose there independently, then life arising isn't the bottleneck. The filter must be later. The eukaryotic transition, intelligence, or something ahead of us. Every piece of evidence for life existing elsewhere is actually evidence that the filter is ahead of us. Every planet we find with microbial life narrows the location of the great filter down toward our futures. This is one of the most counterintuitive ideas in all of science, and I want to make sure it lands properly. Finding life on Mars would be among the worst discoveries in human history. Not because Martian life is dangerous to us, but because it would be strong evidence that the thing that's going to destroy almost every technological civilization is somewhere in our future, not our past. I want to talk about what might lie ahead. The possible filters that would explain why we see no evidence of any civilization surviving to the stage of galactic detectability. The first and most obvious is self-destruction. Technological civilizations develop weapons of mass destruction before they develop the wisdom and governance structures to prevent their use. Nuclear weapons arrived in 1945. Genetic engineering capable of producing engineered pandemics is arriving now. Artificial intelligence capable of autonomous lethal action is arriving now. A civilization that develops these technologies in a political environment of competing nation states with different values and no overarching authority might simply destroy itself before it develops the social technology to survive. This isn't speculation. It's what our own civilization has been navigating for 80 years and what it will continue to navigate with increasing difficulty as the destructive potential of available technologies grows. The probability that a civilization successfully navigates this transition is not obviously high. History of human conflict combined with the trajectory of destructive technology suggests it might be quite low. The second possible filter is resource depletion and climate catastrophe. A technological civilization grows by consuming energy and resources. The transition from fossil fuel energy to sustainable energy requires coordinated global action across political systems that evolve for competition, not cooperation. A civilization that fails this transition might collapse to a pre-industrial level before it develops the capability to expand beyond its home planets. The third filter is what I'll call the transcendence hypothesis. Advanced civilizations might not become detectable and then continue as detectable entities for millions of years. They might instead rapidly transition to forms of existence that are simply undetectable to a civilization at our level. They might migrate to virtual realities that require minimal physical resources. They might develop communication technologies that use methods we haven't conceived of, and that don't look like anything we're searching for. They might modify their own consciousness in ways that make the goals and behaviors of our stage of civilization completely alien to them. On this hypothesis, the galaxy isn't empty of intelligence. It's full of intelligence that has moved beyond the stage where it's detectable by a civilization at our level of development. We're looking for radio signals from civilizations that are still using radio. But no civilization stays at the radio using stage for more than a few centuries. The window of detectability is vanishingly brief. Let me close part one with what I think is the most important and most honest assessment of where all of this leaves us. The Fermi paradox is often presented as a mystery. Where is everybody's? The implication is that the answer is out there somewhere and we just haven't found it yet. More searching, better instruments, more time. But I want to suggest that the most scientifically rigorous interpretation of the available evidence points in a different direction. The silence isn't a mystery to be solved by more searching. It might be the answer itself. The universe might be telling us that we are extraordinarily rare, possibly unique. The only technological civilization that currently exists in the observable universe. Every factor in the Drake equation, when examined carefully with what we actually know about planetary science and the origin of life and evolutionary biology and the sociology of technological civilizations, points toward a number of civilizations that is vastly smaller than the optimists of the 1960s assumed. The rare Earth hypothesis reduces the fraction of habitable planets by orders of magnitude. The improbability of the eukaryotic transition reduces the fraction with complex life. The contingency of intelligence reduces the fraction with technology. The self-destruction scenarios reduce the lifespan of technological civilizations. Multiply these factors together, and the expected number of currently detectable civilizations in the Milky Way might be 1, or less than 1. We might be it. In part 2, I want to take that possibility seriously and explore what it means. Not just for the SETI program or for astrobiology or for our understanding of the universe, but for how we understand our responsibilities as a species, for what it means to be potentially the only consciousness in observable reality, for what the universe has produced in us and what we owe to that extraordinary, improbable fact. Because if we are alone, then the silence of the cosmos isn't just information about what's out there. It's a statement about what we are. And that statement carries a weight that I think we've been avoiding because it's too large to hold comfortably. But I think we need to try. So we'd arrived at this genuinely uncomfortable place together. We'd looked at the Drake equation and seen how every factor that we've learned more about over 60 years has pushed the estimated number of civilizations down rather than up. We'd looked at the rare Earth hypothesis and seen how the conditions for complex life are far more specific and far more improbable than a simple habitable zone calculation implies. We'd looked at the eukaryotic transition and seen how a genuinely rare accident might have been the prerequisite for all complex life on Earth. We'd looked at the contingency of intelligence and seen how nothing about evolutionary history suggests intelligence is the inevitable endpoint of natural selection. And we'd looked at the Great Filter and seen how the silence of the cosmos is powerful evidence that something prevents almost every civilization from reaching the stage of galactic detectability. Now, I want to go deeper. I want to look at what the physics of the universe itself says about the detectability of other civilizations, even if they exist. I want to look at what 60 years of SETI have actually established and what they haven't. And I want to arrive at what I think is the most honest and most important conclusion available from everything we know. Let me start with something that I think gets insufficient attention in discussions of SETI. The physics of signal propagation across interstellar distances and what it means for the detectability of even a technologically sophisticated civilization. We've been broadcasting electromagnetic signals into space since approximately the 1920s. Radio and television transmissions leak into space. Military radar, deliberate transmissions like the Arecibo message. Our radio bubble, the sphere of space within which our most powerful signals have had time to travel, is approximately 100 light years in radius. It's 100 light years. Sounds like a lot. It isn't. The Milky Way is 100,000 light years in diameter. Our radio bubble occupies a volume of approximately 4 million cubic light years out of a galactic volume of approximately 500 billion cubic light years. We've been broadcasting into roughly 100,000th of 1% of the galaxy's volume for about 100 years. And here's the thing about those broadcasts. The signal strength of a transmission decreases with the square of the distance from the source. A signal that's detectable at 1 light year is 100 times weaker at 10 light years and 10,000 times weaker at 100. It's light years. Our television broadcasts, which seem like powerful signals from our perspective, are completely undetectable against the background noise of natural astrophysical sources at a distance of even a few light years without a receiver specifically designed and pointed at us. For a civilization at Alpha Centauri 4.37 light years away to detect our television broadcasts, they would need a radio telescope roughly the size of a small country specifically pointed at our solar system and looking for our specific frequency range. It's not that our signals are going undetected due to lack of technology. It's that the signals themselves are physically too weak at interstellar distances to be detectable without extraordinary targeted effort. This cuts both ways. If we can barely detect our own broadcasts at interstellar distances, then detecting the inadvertent electromagnetic leakage of another civilization at similar distances requires technology well beyond what we currently have. SETI has been searching for deliberate, high-power, directed transmissions from other civilizations, signals specifically designed to be detected. And finding those signals requires that another civilization is actively broadcasting toward us with the intention of being detected. But why would a civilization broadcast deliberately toward us? To broadcast to us specifically, they'd need to know we're here. Our radio bubble is only 100 years old. Only civilizations within 100 light years have even had the possibility of detecting our existence. There are a few hundred star systems within 100 light years. The probability that any of them hosts a civilization that detected our signals, developed a response, and has had time for that response to reach us is quite small. And a civilization broadcasting deliberately to an unknown recipient in all directions simultaneously would need to sustain that broadcast for thousands of years just to give civilizations at thousands of light years distance enough time to detect it and respond. This requires a specific kind of civilization, one that has decided to sustain a galactic beacon across generations and that has the power resources to do so indefinitely. There's no particular reason to think this is common behavior for civilizations, even if they exist. The physics of interstellar communication is simply not as favorable as SETI optimists have assumed. The distances are vast. The signal strengths required are enormous. The time delays measured in thousands of years make conversation impossible. And deliberate broadcasting requires a specific motivation and a specific sustained commitment that may not be typical of how civilizations spend their energy. Now, let me tell you about the detection window problem, because I think it's one of the most important and least publicly discussed aspects of why finding other civilizations might be genuinely impossible, even if they exist. How long does a technological civilization broadcast detectable signals? Our current phase of broadcasting powerful omnidirectional radio signals is approximately 100 years old. Already that phase is changing. We're moving from omnidirectional broadcasting to narrowly directed fiber optic and satellite communication. The radio leakage from our civilization has actually been decreasing over the last few decades as communication technology improves. Tight beam directed communications leak almost nothing into space. A civilization 500 years more advanced than us might produce essentially no detectable electromagnetic leakage whatsoever. Its communication would be completely internal, using methods that don't radiate into space. Its energy might be harvested and used with such efficiency that there's no excess waste heat detectable from interstellar distances. Its technology might be completely invisible to any observatory we can build. And 500 years is nothing on cosmic timescales. Civilizations that arose billions of years before us would have been through their radio detectable phase and through their post-radio phase and through whatever comes after that billions of years ago. The window in which a civilization is detectable might be a few hundred to a few thousand years. Against a galactic history of 10 billion years, that's less than 1 part in a million of a civilization's potential lifespan. Even if the galaxy is full of civilizations, the probability of 2 civilizations being in their detectable windows simultaneously and being within communication range of each other is astronomically small. We might be the radio broadcasting phase of a galactic civilization that has been around in other forms for billions of years. And every other civilization in the galaxy that started broadcasting before us has already moved beyond that phase into something undetectable. The search for extraterrestrial intelligence might be like trying to find other people in a city by looking for people carrying telegram machines. Most people might have moved on to smartphones and the internet billions of years ago. The telegram era was brief. And we happen to build our detectors during the brief window of our own telegram era. Let me now address the anthropic shadow in more detail, because I think it's one of the most important ideas in this entire conversation, and it deserves careful treatment. The anthropic shadow is the observational bias created by the fact that catastrophic events that could have prevented our existence can't be observed by us. We can only observe a universe in which we exist. This means we systematically underestimate the probability and frequency of events that would have prevented our existence. Here's a specific example. Suppose there's a class of catastrophic events, events that occur at some average rate, and that would destroy any technological civilization. If these events are common enough, they represent a great filter ahead of us. Most civilizations get destroyed before they can colonize the galaxy. Now, here's the problem. If these catastrophic events have occurred in the past with sufficient frequency to threaten our existence, then almost all civilizations would have been destroyed before developing astronomical observations. The civilizations that survive to build observatories and search for patterns in cosmic history are, by definition, the ones that got lucky and avoided the catastrophes so far. This means we can't use our own survival as evidence that the catastrophes are rare. We're doing our observations from one of the lucky survivors, not from a representative sample of all possible civilizations. The anthropic shadow hides the frequency of civilization-destroying events from our perspective, precisely because if they were common enough, we wouldn't be here to notice. This has a deeply unsettling implication. We might be living in a false sense of security about the long-term survival of technological civilizations. The apparent absence of obvious existential catastrophes in our recent history might not be evidence that such catastrophes are rare. It might be evidence that we're in the anthropic shadow. The catastrophes are common enough to destroy most civilizations, but we're among the ones that hasn't been hit yet. If the anthropic shadow is real and significant, then the great filter might be an ongoing process rather than a single historical bottleneck. Civilizations are destroyed at some rate by some class of events that are effectively invisible to any civilization that hasn't been destroyed yet. And we're all in the barrel waiting our turn, with no reliable way to estimate from our own experience how likely the event is. Now, I want to address something that I think is the most fundamental and most sobering aspect of the silence. The question of what it means for our understanding of the universe if we are genuinely alone. Not alone in the philosophical or poetic sense, genuinely alone in the physical and empirical sense. The only technological civilization that currently exists in the observable universe. The only place in a sphere, 93 billion light years across, where something is looking back at the cosmos and asking why. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is approximately 10 to the 24th power, a 1 followed by 24 zeros. A septillion stars. If technological intelligence is rare enough to average only 1 civilization per galaxy, then there are 2 trillion civilizations in the observable universe, and we're almost certainly not alone in any cosmic sense. But those 2 trillion civilizations are distributed across 2 trillion galaxies, each separated from every other, by distances of millions of light years. No communication is possible across those distances on timescales that matter for any civilizations. Each is effectively alone in the sense of never being able to make contact. And if intelligence is rare enough to average fewer than 1 civilization per galaxy, then there might be large regions of the observable universe with no civilizations at all. We might be the only technological civilization in the Milky Way, or in the local group, or in an even larger region. What does it mean to be alone in that sense? I want to resist 2 temptations in answering this question. The first temptation is to say it doesn't matter. That questions of meaning and significance aren't determined by how many civilizations exist elsewhere. That our lives and experiences and accomplishments have value independent of what's happening around other stars. This is true, but it's not complete. It matters whether we're alone because it determines the cosmic significance of what we do. If the universe is teeming with civilizations, then our choices here on Earth have consequences only for us. Our actions or inactions affect 1 civilization in millions. The universe doesn't depend on us getting it right because it has many other chances. But if we are alone, or nearly so, the calculus changes completely. Every action we take, every choice we make about how to treat each other and our planet, and the experiment in consciousness that evolution has produced on this small world, has stakes that extend to the entire observable universe. We might be the only thing in 93 billion light years that is capable of understanding the universe's own history, that is producing art and music and scientific knowledge and philosophical inquiry, that has the capacity to propagate life and mind beyond its home planet, or to fail to do so. The second temptation is despair. If we're alone, then the universe is a cold and empty and indifferent place, and our existence is a cosmic accident with no larger meanings. This response takes the absence of other civilizations as evidence of cosmic meaninglessness. But I want to push back on this response directly. The meaninglessness doesn't follow from the aloneness. What follows from the aloneness is something different, and I think something more important. If we are alone, then we are the universe's 1 current experiment in self-awareness. We are the place where the cosmos has produced something capable of looking back at itself and asking why. We are the only repository in the observable universe of the capacity for scientific understanding and artistic creation and moral reasoning and the accumulated knowledge of what the universe is. That's not meaningless. That's the most extraordinary and most consequential fact in the observable universe. Now, I want to address what this means practically for how we should think about our responsibilities as a species. If the universe is teeming with civilizations, then human extinction is a tragedy for us, but not a cosmic one. The universe carries on with its other experiments in consciousness. Other civilizations develop science and art and explore the cosmos. Human failure is human failure, but not universal failure. If we might be alone, then human extinction is different in kind. It's not just the end of our civilizations. It's potentially the end of consciousness in the observable universe. The only place in 93 billion light years where something understands what the universe is goes dark. That is a genuinely cosmic loss in a way that has no parallel. Now, this isn't an argument that we're important in some grandiose anthropocentric sense. It's an argument that if we're alone, our choices have consequences that extend far beyond anything we're used to thinking about. The stakes of getting civilization right are not just human stakes. They might be the only stakes that exist anywhere. The care we take of this planet, the seriousness with which we develop sustainable energy and agriculture and governance, the wisdom with which we manage the technologies that could destroy us, the commitment we make to preserving biological diversity and ecological function, the investment we make in science and in the capacity to understand and eventually expand beyond this world. All of this might matter not just for us, but for the only experiment in consciousness the observable universe is currently running. I don't think this is a burden that should paralyze us with its weight. I think it's a clarification of what we're doing here, why it matters, why getting it right is worth whatever it costs. Let me now address the question that I know is in the back of your mind, because it's in the back of mine. What if we're wrong? What if the universe really is teeming with life and we just haven't found it yet? I want to be honest. That's genuinely possible. The search has been incomplete. The instruments have been limited. The methods have been constrained by our current understanding of how civilizations might broadcast. 60 years of incomplete searching can't definitively rule out the existence of other civilizations. But here's what I think intellectual honesty requires, acknowledging the null result of 60 years of SETI, combined with what we've learned about the factors in the Drake equation, combined with the physical barriers to interstellar communication, combined with the anthropic reasoning I've described, does not point toward the confident expectation of imminent detection. It points toward a sobering alternative. The universe might be mostly empty of intelligence, not because life is impossible, but because the conditions for intelligence are extraordinarily specific and improbable, and because the window of detectability for any civilization that does arise is brief, and because the physics of interstellar distance makes contact unlikely even between civilizations that exist simultaneously. We might search for another 1,000 years and find nothing. And the right response to that possibility isn't to search harder, believing the discovery is just around the corner. The right response is to take the silence seriously as information, to ask what it tells us about our own situation, and to act accordingly. The silence tells us that we might be alone, that consciousness and intelligence are extraordinarily rare in the universe, that the experiment in self-awareness that evolution produced on this small rocky planet might be the most important thing happening in the observable universe right now. And if that's true, then the most important thing any of us can do is to make sure the experiment continues, that we navigate the technological adolescence we're currently in without destroying ourselves, that we develop the wisdom and the governance and the sustainability to carry this experiment forward into the deep future. Not because someone is watching, not because there's a cosmic audience to impress, but because we might be the only ones. Because the universe produced something extraordinary here, and it would be a genuine cosmic tragedy for that extraordinary thing to end, because we couldn't figure out how to stop fighting each other, or how to stop burning our planet, or how to manage the technologies we developed without the wisdom to deploy them safely. The stars are silent. After 60 years of searching, we've heard nothing. And maybe that silence isn't a mystery waiting to be solved by better instruments. Maybe it's the universe telling us something we need to hear, that we're it, that what happens here matters in ways that extend far beyond this small blue world. That the experiment in consciousness, that the universe has been running for 13.8 billion years, has arrived somewhere, and that somewhere is here, and that what it does next is entirely up to us. I find that thought both terrifying and genuinely magnificent. Terrifying because the responsibility is enormous. It's magnificent because what we are and what we might become is worth everything we can give it. The universe is not watching us, but we are watching the universe. And for now, at least, we might be the only ones who are. Meditate on that.